Section 6.3, Volumes by Cylindrical Shells. The volume of the solid in the figure, obtained by rotating about the y-axis the region under the curve y equals f of x from a to b, is the limit of this Riemann sum 2 pi xi bar times f xi bar delta x, which becomes the integral of 2 pi x f of x dx from a to b, where xi bar is the midpoint of the ith subinterval. So notice that in the previous section, we learned how to find the volumes of these types of solids of revolution by using washers and disks. So for this particular one, if we rotate around the y-axis, it goes like this. We keep stacking up washers, and each washer has a tiny thickness delta y, so our integral becomes a dy integral. However, with the cylindrical shell method, when we stack up all of these shells, we stack up from the inside going outward. So that means that we end up with a tiny thickness of the shell, delta x. So the shell method gives us a way of switching from delta x or dx to dy and vice versa. So sometimes when we do the washer or disk method, it becomes hard to integrate because maybe it's hard to solve a function in terms of y. Like for this one, if each washer has a tiny thickness delta y, that means that we need to write our function as an x equals function in terms of y. It can sometimes be hard to solve for x. So that's where the shell method comes in. With the shell method, what we're doing is, instead of constructing a washer or disk and taking the volume of that little washer or disk, we construct a little cylinder around the center, and then we construct another cylinder around that one, and then another one around that one, and then another one around that one, and we nest all of these cylinders together until we get the exact volume of the solid, because we take the limit of the number of cylinders as that number tends to infinity, or becomes arbitrarily large. So the shell method gives us an alternative to switch back and forth between this delta x, delta y, depending on the context of the problem. So we use it when solving for one variable is more convenient than the other, or when it just results in a better integral. Notice that the volume of this shell is equal to the surface area of the shell times whatever thickness the shell has. So some tiny little thickness. So the thickness is just the delta x, but for the surface area of the shell, that's the surface area of a cylinder, almost. Remember that for cylinders, we typically have the top and bottom filled in, so that the surface area becomes 2 pi r squared, because one circle on top, one on the bottom, the area of the circle is pi r squared, plus 2 pi r h, where r is the radius of the cylinder and h is the height of the cylinder. And you get that by unrolling this wrapper around the cylinder. If you flatten it out and unroll it, you get a rectangle, and the height of the rectangle is h, and then the length or the width, whichever dimension you want to call it, and then the other dimension is the dimension that goes all the way around the rim. When you unroll that, that becomes this. So that's the circumference of a circle. So that's 2 pi r. So if we're looking at our cylindrical shells, though, they are empty on the top and empty on the bottom. So there is no 2 pi r squared business. There's only a 2 pi r h. So that 2 pi r h, well, r is the radius of the disk. That's just how far we travel left to right. So that's just the x value that we take the cylinder at. And then the height of the disk is just how far up we go. So that's just the y value. So that's where we get our x value and our y value. But we write y as a function of x, so that we just have, x variables floating around. So we get 2 pi x f of x dx. So let's do an example of all this. How about we find the volume of the solid obtained by rotating about the y-axis the region bounded by y equals 2x squared minus x cubed and y equals 0. So let's see how we can draw this. So here's our nice graph of our function, and I use the word nice very loosely. Okay. Notice that if we were to use washers or disks, in this case we'd have to use washers because we're rotating about the y-axis, so that's over here. We have to rotate. So that means that we would be stacking up all of these little washers, and each one would have a little thickness delta y. So we would have to solve for x in terms of y, so that we only have y variables floating around. Solving for x in this is not so easy at all. So the shell method is going to come in handy. What we should do is try to build a typical shell. So how about if this is a little rectangle? Okay, good. And it's at a particular x value. Then the corresponding shell, let's see if I can draw this. We're going to rotate the region around and then build a shell out of it. Alright, I think my drawings get worse and worse as time goes on. So then here's the inner rim of the shell. Okay, you're not going to be able to see this part going down, so I think I should draw that dashed. Yeah. This is behind, and okay, so it's empty on the top and empty on the bottom, and that's roughly what the shell will be. So if I want to know how far it is from here to here, that's the, from here to here, the x value, that's the radius of the shell. Well, again, that's the x value. So this is x. And then the height of the shell is the y value. So the height is 2x minus x cubed. So I think that's enough information for us to solve this problem now. The volume is therefore the integral from 0 to 2 of 2 pi times the radius, which is x. So that's the circumference of the shell. Then we have to multiply by the height of the shell, which is 2x squared minus x cubed. And then the thickness of the shell, our tiny little thickness dx. So 2 pi is a constant. We pull it out, and we distribute our x, so we get 2x cubed minus x to the 4th dx. And then we do our antiderivative. We get 2 pi times 1/2 x to the 4th minus 1/5 x to the 5th, and we evaluate that from 0 to 2. So that becomes 2 pi times 8 minus 32 over 5, which is 16 over 5 times pi. Let's find the volume of the solid obtained by rotating about the y-axis the region between y equals x and y equals x squared. Well, we seem to love rotating this region around for some reason. So remember that y equals x, I think we used green last time, so let's do that again. That looks something like this. That's y equals x. And then y equals x squared I just left in blue. So that's the parabola opening upward. And then we rotate it about the y-axis. So it rotates around over here. Okay, so let's rotate the green part around. Ends up being something like that. And then we rotate the blue part, the y equals x squared part. Need to fill that in. Okay, so now we get some solid of revolution. I'm not going to actually draw the solid. I'm just going to draw the single rotation over here so that you can see like a slice of the solid. And let's draw one of the potential shells. So we need one rectangle. Oop. Almost got one rectangle. There we go. And we'll rotate this around. And we get a shell. Maybe. We get something like a shell. Okay, that's like roughly the shell. Let's see, it goes from here to here to have some radius x. And the height, well, the height from here to here is x. The height from here to here, the blue part, is x squared. So if I want just the height of the shell, that's the difference between the green height and the blue height. So that's x minus x squared. So that's how tall the shell is. So that means that our volume is the integral from 0 to 1 of 2 pi x, because it's 2 pi r, and our height is x minus x squared dx. So we do that and we get 2 pi times the integral from 0 to 1. By do that I mean distribute the x, and we integrate by taking the antiderivative, and we get 2 pi times x cubed over 3 minus x to the 4th over 4 evaluated from 0 to 1, which is just pi over 6. Let's use cylindrical shells to find the volume of the solid obtained by rotating about the x-axis the region under the curve y equals square root of x from 0 to 1. So we draw the region. I think I want to make this as big as I can. Okay. And I need to draw y equals square root of x. So it looks something like that. And we're stopping at x equals 1 because this thing only goes from 0 to 1. So here's 1. Here's y equals square root of x. However, I'm rotating around the x-axis. So that means when I stack these things up, I'm going to have, if I use the washer method, if I stack up all of these guys, each one has a tiny thickness delta x when I use discs. In fact, yeah, this is not washers, it's a disc, there's no hole. So when I use the disc method, I'm going to have all of these guys with a tiny little thickness delta x. So if I use the shell method, that means that I'm stacking up shells that start from over here, and then they keep going outward. So that means each shell has a tiny thickness delta y. So instead of writing all of this in terms of x, because I'm rotating around the x-axis, and I'm using the shell method, it's the reverse. I'm doing everything in terms of y. Each shell will have a thickness dy. So that means that instead of writing y equals square root of x, I should write x equals y squared when talking about this function, because I'm going to have to solve for x, because I have to write it in terms of y. So here is our height I forgot to write. Let's look at a particular shell. So how about at some y value y, let's see if I can draw a nice rectangle, and then we can try to imagine what the shell would look like, because I don't feel like drawing another rotated shell. Well, if the shell goes around over here like this is what the shell would look like. Then here's the radius. It's the y value this time, because this is the shell, right? From here to here is the radius of the shell, and that's the height of the function. So then that means that this is how tall the shell is. So if I want to know how tall the shell is, that's this right over here. It's a little bit more tricky to figure out. From here to here is 1. From here to here is x equals y squared. That's the x value from here to here. So if I use that information, I know that this is y squared, and I know that all the way is 1. That means that this is the difference, 1 minus y squared. So we have enough information now to do our integral, because now we know what the radius and the height of the shell is. So our volume will be the integral from the bottom, which is 0, to the top, which is 1. So it's a coincidence that x is also from 0 to 1. If this was a 2 over here, then I would be integrating from 0 to 2, because I'm doing it in terms of y. So I stack up my shell starting at 0, ending at 1 for y. I have 2 pi times the radius of the shell. We said the radius of the shell was y, so 2 pi times y, and then times the height of the shell, 1 minus y squared. So then this equals 2 pi times the integral from 0 to 1 of y minus y cubed dy, which is equal to 2 pi times the antiderivative, y squared over 2, minus y to the 4th over 4, evaluated from 0 to 1, which is pi over 2. So the integral wasn't that bad. However, it was way easier using the disk method. We didn't have to switch from x to y. We didn't have as complicated of an integral, and we also didn't have as complicated of a setup over here. So the shell method is not always better. It's only better if switching actually saves you time. Okay, let's find the volume of the solid obtained by rotating the region bounded by y equals x minus x squared and y equals 0 above the line x equals 2. So first let's draw our region. So this looks something like this, because it's the parabola y equals x minus x squared. What's going on over there? There we go. And we need to try drawing a cylindrical shell somehow. So how about we get this? We need a lot of space because we are rotating about the line x equals 2. And the way that I drew this, this is 1. So 2 is going to be much farther. So I'll draw my parabola again. It's bounded by y equals 0, so it never goes below this line over here, so I don't have to worry about these ends. So this is at 1. Then it needs to revolve around x equals 2. So that'll be over here. This could be x equals 2. This is my y-axis and my x-axis. And when this thing revolves around this thing, it ends up reflecting across, and it looks like this. spins around. Obviously, it's going to be three-dimensional, but I'm not drawing the rest of it. I'm just drawing one spun flat part, so we can just look at a slice. So let's see if I can somehow manage to get a shell out of this. Well, we'll draw a rectangle. Maybe. Something like that. And then the rectangle spins around, so let's put our rectangle over here. And let's see if I can spin it. Nah, that was almost, but not quite. There we go, that's a little better. And this is my bottom part of my shell. Okay, now we need the inside, because the inside's got to be empty. And that's the bottom. That's the top. Okay, so those are the sides of the shell. And then on the bottom, so you could see like the inside. Okay, that's like a almost half decent shell. If I go from here to here, that's just the x value along the curve. So that's from here to here. I would like to know what the radius of the shell is, which is from here to here. Well, if from here to here is x, and from here to here is 2, then from here to here is the difference. So this thing, it'll be 2 minus x. So that's the radius of the shell. And then the height of the shell is just the y value, x minus x squared. So again, we have now enough information to do our integral. We get that the volume is the integral from, let's see, we're doing x now, so we'll go from 0 to 1, because that's how far we're stacking up these shells. So we get 2 pi times the radius. In this case, the radius wasn't just x. The radius, because the shell was over here instead, it wasn't just around the y-axis, it was around x equals 2. So we had to make a big adjustment and find that the radius was 2 minus x for the shell. But the height was still just the y value without having to worry too much. So that was just y equals x minus x squared, because we didn't move anywhere really. So then we get 2 pi times the integral from 0 to 1 of x cubed minus 3x squared plus 2x. We evaluate that by taking the antiderivative, and we get 2 pi times x to the 4th over 4 minus x cubed plus x squared, all evaluated from 0 to 1. And that's pi over 2.